Okay. Okay, so today is going to be the first day when we'll see actual geometric applications of modular forms. And tomorrow, but today is still going to be, everything is going to be very classical. But tomorrow I will talk about the work on sphere packing and on universal optimality. So this will be something, a slightly different appearance of modular forms. But today it's going to be all about theta functions. And I will start with a very kind of simple version of that. So the unary theta function, which is just the sum, the generating series for, well, for the subsequence of all squares, so to speak. So it is this generating series, so just the sum of q to the power n squared over all integers. And as I've mentioned in the first talk, it is a modular form, but now we're actually going to prove it. So clearly, because of the way I wrote it, it's already one periodic, because q, well, it's not written in the slide, but it's still e to the 2 pi I tau. So what we need to prove is some other transformation law. And in this case, unfortunately, it's not, well, not unfortunately, it's not a modular form for the full modular group, but it is a form for a subgroup of some finite index. So precisely we'll prove now that the function theta satisfies this transformation law. And then I will say why this implies it's a modular form for the group gamma not 4. So the proof is based, the proof of this result, and actually all the other main theorems in this lecture is going to be based on Poisson summation formula. So I'll recall very briefly a version of it. So let's say you have a function which is nice, a function on the real line with complex values, which is, we assume it to be smooth and rapid decay, and having rapid decay. So it's a Schwarz function. And for this function, we define the Fourier transform with the following normalization. So it's a standard Fourier transform with a 2 pi I minus 2 pi I in the exponent. And I mean, this normalization is very convenient for Poisson summation formula, because then it simply becomes this identity. So it's the sum over all integers of shifts at a point x by n of the values of f at these shifts is equal to the sum over all integers. So it's a Fourier series now with coefficients which are given by the values of the Fourier transform. And kind of, well, the way I said it already suggests a way to prove it. So we're looking at the left-hand side as a function of x, and because of the way it's written, it's already periodic. So it's a function on the circle on R mod z, and then we develop it into its Fourier series. And actually, the coefficients turn out to be exactly the Fourier transform of the original function. So it's very easy to prove for Schwarz functions. I mean, it's not, one can assume less about f, but for the purposes of this talk, it will suffice. So now we can prove the claim that I made before. So we want to prove this identity, and what we do is we simply apply the Poisson summation formula to the Gaussian. So we take f of x to be the function e to the minus pi t x squared. And if I had t equals 1, then one knows that this would be an eigenfunction with eigenvalue 1. So because of that, you can compute the Fourier transform of this v-scaled version. And it turns out to be exactly, well, again, a Gaussian with the parameter t inverse, but it's also multiplied by t minus 1/2 because of the rescaling. So then you apply the Poisson summation formula, and well, actually, you take a special case of it when you put x to 0. And then the formula reads, so this sum on the left of Gaussians, so this sum e to the minus pi n squared t is equal to t to the minus 1/2 times a similar sum, but with parameter 1 over t. So if you kind of change t, you rotate it by I, you recover more or less this identity, except well, you recover it for tau on the imaginary axis, but because these are two analytic functions, so two complex analytic functions, you know that this is true for all tau in the upper half plane. Okay, so it's not exactly the type of matrix we looked at before. So what we have proved is that, first of all, theta is T invariant, so it's one periodic, and it satisfies a modular transformation law with respect to this matrix W4, which is not in SL2Z, but it's not really a problem because it still defines fractional linear transformation, and we proved that it satisfies the transformation law. So what we can do is, well, if we apply some composition of these two matrices, it might happen that fractional linear transformation actually is equal to some transformation from SL to Z. And that's exactly what happens. So if you take the product W4 TW4, then it's given by this matrix, which is not unimodular, but the way it acts on the upper half plane is the same. It acts in the same way as this matrix, which is unimodular. And then one can further prove that these two matrices T and this new matrix, they generate they generate the full group gamma naught 4. I'm not sure why I wrote -1 here, but it doesn't matter. So I'll just remind briefly that gamma naught 4 consists of all matrices with determinant 1, 2 by 2 matrices with determinant 1, and such that well, if you write it as A, B, C, D, then C should be divisible by 4. Okay, so now we haven't quite proved, well, I mean, we haven't defined what a modular form of half integral weight is, but if you take a fourth power of theta, then from what I said here, one can prove that actually is a modular form of weight 2. And I'll use it as an exercise. So what's interesting is that the powers of theta, they're generating functions for well, somewhat well-known fixed sequence of numbers, which is the number of representations of an integer as a sum of k squares. So in particular, because of the fact that we know that this fourth power of theta is modular, and we can construct a basis for this space of modular forms, we get for free an identity. And in this case, it's actually easy to prove that the space here, M2 gamma naught 4, is two-dimensional, and that it's, well, once you know that it's two-dimensional, well, you can easily verify that these two functions belong to this space and they're independent, linearly independent. So some simple linear algebra shows that one must have this identity. And actually, if you write it out for what does this mean for this sequence R4 of n, it's an identity due to Jacobi, which is, well, I mean, this is more or less the way he derived it. So, and once you look at this identity a little bit, you see that it's a sum of all divisors of n, which are not divisible by 4. So in particular, there is always 1 in this sum. So it shows that R4 of n is always at least 8, which implies that there is at least one representation of n as a sum of 4 squares. So we get Lagrange's 4 square theorem for free. And similarly, we can take higher powers of theta. So if you take 8th power, then we land in M4 gamma naught 4. So it's weight 4. And then again, we use the Eisenstein series of weight 4. And one can show very easily that these three functions actually, again, are modular forms of level 4. And so again, linear algebra tells you that we have to have some identity between theta to the power 8 and these three guys. And once you work it out, you get this representation for R8 of n. Okay, so there's an interesting thing going on here, which if you look a little bit at these two formulas, so if you divide by 8, so if you scale R4 of n in such a way that R4 of 1 is 1, if you divide R8 of n by 16, so that again it's 1 and it's 1, then you get something which is more or less a Dirichlet convolution. I mean, it is directly in this case, and it's somewhat less obvious that it's also the case here. But what this shows is, in fact, you get, this shows that these sequences R4 of n divided by 8 and R8 of n divided by 16 are multiplicative. So what this means is that they satisfy this identity for all co-prime m and n. So if you have m and n are co-prime, then the A of the product is equal to the product of the values. And one can ask a natural question. Well, I'm not sure if it's too natural, but certainly one can ask it. What other values of k are such that this sequence is multiplicative? And that's exactly the content of this exercise. So it turns out that if you normalize Rk of n in such a way that the first number is 1, then the sequence is multiplicative if and only if k is 1, 2, 4, or 8. And so the proof of this exercise is not that hard, but there's interestingly there's some coincidence between these numbers and the dimensions of division algebras, norm division algebras over R. And this actually suggests a more complicated way of proving multiplicativity in each of these cases, which I haven't actually followed through. So, which more or less requires one to look at, well, integers. So it more or less requires one to do something close to unique factorization of integers, Gaussian integers, then Lipschitz quaternions, and I'm not sure what the name for this naive definition of integral octonions is. So there's actually two ways of trying to prove that it's of proving that these sequences are multiplicative. Okay, but I mean, I don't want to spoil too much. So now we turn to the geometric side. So instead of looking at one-dimensional lattice Z inside R, we can look at higher dimensional lattices. And I'll just briefly recall what they are. Well, some notation, but I'm sure all of you know it. So we call a lattice integral if all the inner products are integral. We call it even if all normed squares of vectors are even. And we define the dual lattice by the requirement that it has integral inner products with all the vectors of the original lattice. So we call a lattice unimodular if it's equal to its own dual, and for integral lattices it's equivalent to requiring that the covolume is 1. Okay. So the nice thing about Poisson summation formula is that it takes almost no time to generalize it from one-dimensional case to the d-dimensional case. And also the proof that I gave, the one-line proof, also works almost the same way. So instead of looking at one-dimensional, the function on R, look at the function on RD, which is still nice, rapidly decaying and smooth. And then the Poisson summation formula becomes this claim. So again, we symmetrize on one side, we symmetrize over all shifts by the lattice, and on the other side, we have kind of a Fourier series. And well, I mean, just to make sure we have this, I mean, the notation is more or less the same as in one-dimensional case, just normalize by minus 2 pi I, and normalize the Fourier transform by minus 2 pi I in the exponent. And the proof is more or less, I mean, it's almost verbatim the same. You just have to consider instead of the one-dimensional torus, the d-dimensional torus, and you do the Fourier series on that space. Okay. So what we can do now is, well, we have very easily, we easily proved the transformation law for the Jacobi theta function in one dimension, but let's try to do the same thing with the lattice. So let's say we have an even unimodular lattice, so that, well, when we apply the Fourier transform, we get, okay, I mean, I'll explain later why we do it. So the claim, first of all, well, we'll prove two facts at the same time. First, that the dimension has to be divisible by 8. And second, that the theta function associated to this lattice, which we just define as a kind of a weight enumerator for the lengths in the lattice. So it's a sum of q to the power of the square, the length squared divided by 2. So because lambda is even, this will always be an integer. So this would make it automatically periodic. But then we'll actually prove that this is a modular form of weight d over 2 for the full modular group. Okay. So how does the proof work? It's the same with a slight difference. So we apply again the Fourier transform. Oh, sorry, we apply the Poisson summation formula to the Gaussian, and then it gives us exactly this identity. So if we rewrite what it means in terms of the theta functions we introduced, it becomes theta function of the original lattice at point tau is equal to the theta function of the dual lattice at point -1 over tau with the automorphy factor and well weighted by the 1 over the covolume of the lattice. Since we're looking at even unimodular case, this tells us that these two lattices are the same and that this covolume is 1. And also because it's even, we know that this function is periodic. So we get from this identity, we get also the identity here. So we get this, the value of the lattice, of the theta function of the lattice at the points 1 - 1 over tau and tau are related. And because of the fact that, well, if you look at this transformation, tau going to -1 - 1 over tau, it's a cyclical Fourier 3. So if you apply it 3 times, you get back again. So now we write down 3 such identities, and then we multiply them all out. And then the theta lambda values will cancel out. And what we're left with is the identity between the automorphy factors. So we get that the product of these 3 things should be 1. But one can actually work this out. It's not so hard. So you can, for example, plug in some number tau and then compute directly what this means. So there's something, well, which I'm cheating a little bit. So I didn't tell you what to do with the branch cuts, but we always take the branch cuts in such a way that the logarithms of the real numbers are real. So then this is all well defined. And then one can calculate that this number is actually e to the -2 pi I d over 8. So it has to be equal to 1, so d has to be divisible by 8. And once you know that d is divisible by 8, this factor here becomes just t to the power -d over 2. So in particular, we prove, we get that because this transformation, or actually this transformation together with t generates a full group, we get that the theta function is modular of weight d over 2. Okay. So we can get some simple applications of this result. First is very naive, so we can compute the theta series of the E8 lattice. And well, the definition of the E8 lattice is given here. But what you need to know really is it's an even unimodular lattice in 8 dimensions. Once you know that, because of the fact that its theta function is modular, and the space of modular forms of weight 4 here is 1-dimensional, we get for free that this has to be equal to E4. So one thing, maybe I haven't quite emphasized it before, but because of the way we defined it, theta function always has a Fourier expansion starting with 1, because we always sum up, we have the 0 vector in the lattice. So we always get a constant term from that, and it's 1. So then it has to be equal to E4. And of course, it's not a very good choice of notation, but what can you do? So E4 here is an Eisenstein series, but E8 is a root system. So, but what you get from here is that the number of vectors of length square root 2n in this in the E8 lattice is equal to 240 multiplied by sum of cubes of divisors of n. So kind of going back to the exercise that I gave, there's a cute fact that's related to it. So if 240 is, okay, so one can define a notion of what an integral octonion is. And it turns out that 240 is exactly the number of sort of units in that non-associative algebra. But then the condition, the fact that sigma 3 of n is again multiplicative once again can be interpreted as some sort of uniqueness of factorization of those integral octonions. But I won't say much about this. Okay. So now the real application, well, we already got one application, which is a very simple proof of the fact that even unimodular lattices, if there is an even unimodular lattice in dimension d, then d has to be divisible by 8. So what we can also do is we can calculate, we know that the theta function is a modular form, and we know more or less precisely what the space of modular forms for SL2Z looks like. So what we can get from the formula, from the fact that it's a modular form and it has an expansion starting with 1, is an approximation to the number of a number of vectors of length square root 2n in the lattice when n is sufficiently large. And so it turns out actually that it doesn't depend on the lattice that much. For this, I want to say a few words about cusp forms. So, I mean, there's something, I haven't told you much about the distinction between Eisenstein series and cusp forms and why one actually has to look at those things separately. But one of the reasons why they behave very differently, if you look at an Eisenstein series, the coefficients there grow like n to the power k minus 1. And as it turns out, the cusp form has much smaller coefficients. And well, this is a subject of very deep theory, but there is a simple estimate due to Hecke that you can prove, and it's very simple proof. So if you look at any cusp form of weight k, then its Fourier coefficients grow, they're bounded by some constant times n to the power k over 2. And the proof is very easy. So what you do is you consider the function, this function, which is now, it's real analytic, but it is gamma 1 invariant. So this is the same function that was mentioned in one of the exercises yesterday. So, well, if we know that f is a cusp form, we know that it's exponentially small at infinity. And if you recall what the fundamental domain for the group gamma 1 looks like, it's, well, if you cut off the bit at infinity, it's a compact region in the upper half plane. So there, any continuous function is bounded. But then, because f originally is a cusp form, then it's also rapidly decaying at the cusp. Well, I'm kind of using terminology I haven't introduced. So it's rapidly decaying at infinity. So it means that the function itself is globally bounded. Okay, so let's say f is bounded by some constant c, but then you can just compute the Fourier coefficient am by this integral. And if you do this integral at height 1 over m, and just estimate everything by absolute values, you get this estimate. So you get with explicit constant, well, the explicit dependence on this upper bound, you get an estimate for the Fourier coefficients. So the only thing we actually need about this is that this k over 2 is smaller than k minus 1. So let's say we have an even unimodular lattice in dimension 8L. Then we'll prove that the number of representations is asymptotic to the sum of divisors to the power 4L minus 1 with coefficient here, which the way it's written, it's not clear why it's positive, but it is. And this coefficient doesn't depend on the lattice. And the proof is very easy. You just look at the theta function. You know it starts with 1 plus something plus q plus some coefficient times q plus so on. So you just, by definition, you know that if you subtract the Eisenstein series E4L of tau, what you're left with is a cusp form. And that cusp form, well, by the estimate from previous slide, its coefficients grow at slower than n to the power 2L, at least they not faster. And the sum of divisors is greater than that, so definitely this term dominates, and we get the asymptotic claim here. Okay. So now there is another application which is a lot more interesting, which is, so we know that the space of modular forms is finite dimensional. In particular, and because of the way, because of the way it's constructed, one can actually prove that there is a sort of an echelon basis. So if you specify any of the first m coefficients, any values for the first m coefficients, there is a unique form of these first m coefficients. So this is very easy to prove using delta function, but maybe I'll leave it as an exercise. So if the dimension of the space is m, then by this linear algebra argument, there is a unique modular form with a Fourier expansion that starts with 1 and doesn't have any, all the coefficients between zeros and m's are 0. So, and if there is even unimodular lattice lambda with such a theta function, we call it extremal. So it's, one might think that, okay, so it cannot vanish also at q to the m, but that's actually a non-trivial fact. So it's, if you define the next two coefficients, so this is a well-defined form. It depends only on L. And all extremal lattices have the same theta function simply by definition. And if you look at the next two coefficients of the Fourier expansion of this modular form, then actually one can prove certain things. So first of all, one can prove that the next coefficient, the one which corresponds to vectors of length square root 2m, is strictly positive, which means that, well, in particular, well, extremal lattice has these vectors, but also anything non-extremal also has vectors which are shorter than square root 2m. So we get that any even unimodular lattice has a vector of length at most square root 2m. So this result is, you can easily verify it in each dimension by itself, but if you want to do it for all dimensions, you need some kind of argument. And the second bit is, the coefficient right after that, PL, it turns out that at some point it becomes negative. So Mallows, Odlyzko, and so on have proved that exactly this. So they prove that this coefficient becomes negative as L gets sufficiently large. And in particular, this means that there are no extremal lattices in high enough dimensions. So I should mention that, well, at least this is a non-empty definition because there are extremal lattices, in particular, well, when the dimension is, when m is 1, any even unimodular lattice is extremal. But also, well, we have explicit examples. So the E8 lattice is extremal and the Leach lattice is extremal. And unfortunately, as far as I know, the biggest extremal lattice known is 80-dimensional. And the upper bound coming from this theorem is somewhere around 160,000. So actually, it's not clear how many of the extremal lattices should there actually be. Okay, so I won't actually give a proof, but I'll briefly explain what goes into it. So by certain manipulation of generating series, one actually can compute this coefficient AL. So, you can imagine, you really just have to do some linear algebra to compute it, but one can actually turn it into a formula. And in the particular case, the formula depends on the value of L modulo 3. So when L is divisible by 3, we get this identity, which looks a bit complicated. But the only thing we really care about is non-negativity. And that is easy to see here because all the terms inside the big round brackets have non-negative Fourier, only non-negative coefficients, actually strictly positive coefficients in the Fourier expansion. So for E4, this is clear. For the derivative of E4, it's also clear. But this thing is also clear because we take 1 over 1 minus q to the n to some positive power. So it has, again, strictly positive terms in its expansion. So this automatically gives us the inequality from Ziegel's theorem. Now the next coefficient is a lot more complicated, but
just to clarify notation,
yes.
What is brackets q to the k?
Oh yes, sorry. This is, I'm using notation for picking out the case coefficient in the Q expansion of the expression in the brackets. So Yeah, so this is, you take this Q series, you expand it out, and you pick its case coefficient. But actually, all coefficients of this Q series are going to be positive. So in particular cases also. And that shows it's positive. Actually, this, this coefficient grows rather quickly with K. And one can show very precise asymptotics for it. And more or less that's involved in proving the claim of Dlisco, Malus, and so on, that the PL is negative starting from some dimension. So one has to work out the asymptotics of these two numbers, and then one can figure out when it starts going wrong. Okay, so far we have only used like a boring set of functions where we just sum up kind of weight 1 for each vector in the lattice, but we can do some, we can put some non-trivial weights, and one simple generalization of the usual zeta lattices, zeta function is we put a weight which is a harmonic homogeneous polynomial in the variables. And then, well, whenever we have such a thing, and even unimodular lattice, we can define now a zeta function depending on lambda and p, which is the sum of overall vector, again, over the lattice, but now for each q to the power the square of the norm divided by 2, we also put a weight which is the value of the polynomial in question. So more or less the same proof works, and one can show that this zeta function is again a modular form, but now it's of different weight. So it becomes dimension divided by 2 plus m, where m is the degree of this homogeneous harmonic polynomial. And because of the way, well, I kind of forced the degree to be greater than 0, well, by way of defining it here. And it's homogeneous. So actually, if you look at the 0 vector in the lattice, the coefficient it contributes is 0. So automatically, if we show that it's a modular form, it's going to be a cusp form. And well, I'll just indicate the proof is, again, you apply Poisson summation formula, but now you take this function, and then there's a nice identity which tells you that this is actually, if you put tau to be I, this function is actually, again, a Fourier eigenfunction with eigenvalue which is equal to I to the power m, where m is a degree. And now, again, if you do this rescaling argument, it tells you that the Fourier transform of this function here is I to the m times this vector times the original thing. And you just follow the rest of the argument the same way. Well, because we already know that d is divisible by 8, this I kind of cancels out. Well, okay, maybe it doesn't quite cancel out for odd m, but for those it vanishes anyway. So we get the modular form exactly in this space. And once again, because its first coefficient is 0, we get also that there is a cusp form. So because of the way we defined it, we now have the freedom of choosing the lattice and the polynomial. And one application which was kind of briefly mentioned in Frank's talk, well, at least the corollary of this application is we can look at the lattice and try to look at its shells, so all the vectors with given lengths, and try to see how good of a configuration that is in terms of spherical designs. So, well, you already saw the definition of spherical designs today, but just to recall. So it's just a collection of endpoints on a sphere such that if you integrate any polynomial of degree less than or equal to t over the normalized to back measure on the sphere, you get the same value as the average over these points. And there's some simple representation theoretic argument which shows that it's enough to show it for harmonic polynomials, for homogeneous harmonic polynomials. Okay, so now we can use our theorem about the weighted zeta function. And for example, we get very easily the fact that the E8, all the shells of the E8 lattice are 7 designs. So what we do is we apply the theorem. If P is harmonic of degree D, well, so we need to check, so to check that something is a spherical 7 design, we need to check it against all harmonic polynomials of degree well, odd degrees don't really matter, but between 1 and 7. So if, let's say it has degree d, then we know by the previous theorem that the weighted theta function lands in the space of cusp forms of weight 4 plus d. And now we know the dimension, we know the dimension of this space in each case. And it tells, well, the formula tells us that this space is actually trivial for d less than 8. So they all vanish, and it doesn't matter which polynomial you take. Okay, so actually there's something a bit funny, because if you look at the dimension formula, it also tells you that the space S14 of gamma 1 is trivial, and that would correspond to harmonic polynomials of degree 10. So the E8 lattice is a bit, well, the shells of the E8 lattice are interesting because they vanish, so they are spherical designs for all harmonics of degree less than 8, and also for degree 10, which I think Venkov used to call this a 7.5 design. Of course, the odd design condition is kind of trivial because in the lattice you always sum up over pairs of opposite points, so they all kill odd degree polynomials, homogeneous odd degree polynomials. Okay, so the next thing is not quite an application, but it's kind of a reformulation of a famous conjecture about modular forms, well, about the delta function. So Lemmer has conjectured that the Fourier coefficients of delta are always non-zero. And there is a kind of a way to reformulate this conjecture in geometric terms, which may or may not be useful to get any insight into whether it's true or not. So Lemmer's conjecture turns out to be equivalent to the statement that, well, we just saw that the E8 lattice was a 7 design. Each shell of the E8 lattice was a 7 design. But actually, if you can find at least one shell which is an 8 design, this would be a counterexample to Lemmer's conjecture. So it's equivalent to the claim that this is never an 8 design. And the proof is more or less the same idea as before. You look again now at harmonic polynomials of degree 8. You have to check that the first shell is not an 8 design. So at least for one polynomial, it doesn't vanish. And then it shows that the weighted theta function for that polynomial is a multiple of delta of tau. And so whenever you have a vanishing coefficient in delta of tau, you would have an 8 design. And if in the other direction, if you never have an 8 design, you can't have vanishing here. And in fact, you don't, well, because of the fact that it's not just a 7 design, but a 7.5 design, whenever all the harmonic polynomials of degree 8 vanish, when you average over a set of points in the E8 lattice, also the 9, 10, and 11 design goes through. So it doesn't really matter. I mean, all these conditions are equivalent. But as far as I know, no one expects to have any coefficients which are 0. Okay. So next is the application, which is a real application, but I won't tell you all the details. But I already said what the design is. So a spherical design is called tight if it matches the so-called lower bound or the absolute bound. And well, usually people separate the even and odd case, but I decided to put it in one formula. So it maybe is a bit ugly, but it doesn't really matter because, well, one knows, so due to the work of Banai and Damerel, that tight designs actually exist. They exist very rarely. So for T, so T is the strength of the design. Outside this set, there are no, the only tight designs are the regular polygons. Now for the values of T in this set, there are some distinctions. So there's exactly one tight 11 design, which is the shortest vectors of the Leech lattice. And then for T equals 1, 2, and 3, there is a very simple classification. So that kind of leaves 3 parameters which are complicated, 4, 5, and 7. And it's known that 4 and 5 are more or less equivalent. So really it's 5 and 7. And not that much is known. Well, I mean, there are lots of cases when we can prove there are no tight designs, but the only known examples, more or less, come from either the E8 lattice or the Leech lattice. So if you look at these dimensions, 6, 22, 7, 8, 23, these are kind of avatars of the E8, well, of the root lattices or the Leech lattice. And the only outlier is really the icosahedron in dimension 3. So the application that I wanted to say is that, well, first of all, the general theory tells you that if there is a tight 5 design in dimension greater than 3, then the dimension itself has some arithmetic conditions on it, and it has to be too smaller than a square of an odd integer. And the two examples that are known correspond to this parameter m being 1 and 2. And there is a nice work by Banai, Munemasa, and Venkov, who proved that the next two cases, m equals 3 and 4, cannot, well, there are no tight 5 designs in those cases. And what they did is the proof is based on analyzing the lattice generated by the tight design. And in the case of 3, I think, which corresponds to a potential 5 design in R47, what they did is they constructed a certain unimodular, even unimodular lattice out of the tight design in one dimension higher, and they showed that that unimodular lattice has a zeta function starting with the following sequence of numbers. And well, you have enough information from here to deduce, well, to get a contradiction, because you have 4 coefficients and the dimension in weight 24 is 3. So you kind of, these numbers can't be arbitrary. And in fact, they cannot come from any lattice, which you get from this linear algebra computation. So that I leave as an exercise. And maybe we'll want to stop here.